So Chapter 2, Measurement Part 2. Now, we introduced measurement of physical quantities and their SI units in Form 1. One very important physical quantity is length, which we measure in meters. The common instrument for measuring length is the meter rule. The most accurate ruler can measure up to a millimeter of length. This is called the least count. But in science, we need to make measurements smaller than that. Two important instruments used to measure very small lengths to a highly accurate degree is the vernier calipers and the micrometer screw gauge. We start with the vernier calipers. A vernier calipers is used to measure the length, thickness, diameter, and depth of an object and to measure the internal and external diameters of a hollow cylinder. This instrument can measure dimensions up to 0.1 millimeter or 0.01 centimeters. The two scales on the vernier calipers are the main scale and the vernier scale. The main scale is a long, thin steel strip with a jaw J1 at one end and is graduated in millimeters. The vernier scale is a graduated movable steel strip with a jaw J2 that can slide over the main scale. Generally, the vernier scale has 10 divisions marked on it. The vernier scale can be fixed at any position on the main scale with the help of a screw. The jaws J1 and J2 are parallel and projected on either side of the main scale. The lower jaws are called the outside jaws. They are generally used to measure the length or thickness of a given rod and diameter of a sphere or a cylinder. The other jaws are inside jaws and are used to measure the internal diameter of a hollow cylinder or pipe. There is a thin, long strip T1 attached to the vernier strip at the back of the main scale. This is used to measure the internal depth of a hollow tube or cylinder. The object to be measured is placed in between the lower outside jaws. Whenever we use a vernier calipers, we need to first find the least count and the zero error of the instrument. Least count of an instrument is the smallest measurement that can be recorded accurately with it. To know the smallest measurement, we must first find out the number of divisions on the vernier scale and the value of one main scale division. In this case, they are 10 and 1 millimeter respectively. Least count is then given as the value of one main scale division over the number of divisions on the vernier scale. This will be 1 millimeter over 10, which is equal to 0.1 millimeter or 0.01 centimeters. Now the zero error. Sometimes, when the movable jaw is brought in contact with the fixed jaw, the zero of the main scale does not coincide with that of the vernier scale. This is a mechanical error and is referred to as the zero error of the vernier calipers. Depending on the position of the main scale, the zero error can be positive or negative. Consider these three vernier calipers A, B, and C. In vernier calipers A, the zero of the vernier scale and that of the main scale coincide. Therefore, this calipers has no zero error. In vernier calipers B, the zero of the vernier scale is to the right of the zero of the main scale. This vernier calipers is having a positive zero error. To get the zero error of these vernier calipers, we first note the division of the vernier scale that coincides with any division on the main scale. In this case, we have 4. We then multiply this with the least count of the vernier calipers. This gives us 0.04 centimeters. The readings taken by these vernier calipers will be greater than the actual measurement by 0.04 centimeters. The vernier caliper C is having a negative zero error. To get the zero error here, first we note the division of the vernier scale that coincides with any division on the main scale. In this case, it is 6. We subtract this from the number of divisions on the vernier scale. Then we multiply this difference with the least count and assign a negative sign to the final value. So here we shall have 10 minus 6 times 0.01 centimeters. That will give us negative 0.04 centimeters. The readings obtained by these vernier calipers will be less than the actual measurement by 0.04 centimeters. After finding the least count and the zero error of the vernier calipers, we calculate the readings using the formula. Observed reading is equal to main scale reading plus the coinciding vernier scale division times the least count. Then we calculate actual reading is equal to observed reading minus the zero error. And remember, zero error can be positive or negative. For example, let us determine the length of this rod. The first thing is to find the least count of the vernier calipers. And we know our vernier calipers has a least count of 0.01 centimeters. Then we check if the vernier calipers has a zero error. In our case, it appears to have a positive zero error. We calculate how much that is. The coinciding vernier scale division is 6. So we multiply that by 0.01 centimeters to get a zero error of positive 0.06 centimeters. Now we are good to go. We fix the rod in between the outside jaws J1 and J2. We note the main scale reading. It's 4.6. Then we note the coinciding vernier scale division. It is 3 in our case. We calculate the observed reading using our formula. 4.6 plus 3 times 0.01 will give us 4.63 centimeters. And then we calculate the true reading. 4.63 minus the zero error, positive 0.06. And that gives us 4.57 centimeters. The next instrument is the micrometer screw gauge. A micrometer screw gauge is an instrument used to measure the diameter of a thin wire or the thickness of a metal sheet up to an accuracy of 0.001 centimeters. It has a U-shaped frame with a flat end A called the stud. There is a long cylindrical nut at the other end which is threaded from inside. There is a screw with a flat end B that can move inside the nut by rotating a hollow cylinder or thimble provided at the other end. A reference line graduated in millimeters is drawn on the cylinder attached to the nut. This reference line is called the main scale. The thimble is also graduated and is divided into equal parts, usually 50 or 100. This graduated part of the hollow cylinder is known as the head scale or the circular scale. There is a ratchet attached to the screw by a spring. This is used to turn the screw. In order to use a micrometer screw gauge, we need to know its pitch, least count, and the zero error. The pitch of a screw is the distance traveled by the tip of the screw when the head of the screw is rotated once. That is, the pitch is the distance between two consecutive threads. To determine the pitch, we rotate the screw 5 times and record the distance moved by the main scale. In this case, it is 5 millimeters. The number of revolutions is equal to 5. So, pitch is equal to the distance moved by the thimble on the main scale over the number of revolutions. In this case, pitch is equal to 1 millimeter or 0.1 centimeters. Least count of a micrometer screw gauge is the smallest distance moved by the tip of the screw when the screw turns through one division. It is given by pitch over the number of divisions on the circular scale. In our case, it will be 1 over 100, which is equal to 0.01 millimeters. Just like in the vernier calipers, sometimes on bringing the flat end of the screw in contact with the stud, the zero of the circular or head scale does not coincide with the zero of the main scale. This is a mechanical error and is referred to as the zero error of the micrometer screw gauge. Again, depending on the position of the zero of the circular scale, zero error can be positive or negative. Consider these 3 screw gauges A, B, and C. In A, the zero of the circular scale and that of the main scale coincide, so A has no zero error. In B, the zero of the circular or head scale is below the reference line of the main scale. This screw gauge is having a positive zero error. To calculate the zero error, we note the division of the circular scale that coincides with the reference line. It is 2. Zero error is calculated by multiplying this coinciding value with the least count. In our case, we shall get 0.02 millimeters. So it will give a reading larger than the actual value by 0.02 millimeters. In screw gauge C, the zero of the head scale is above the reference line of the main scale. This screw gauge is having a negative zero error. To calculate this error, we note the division of the head scale that coincides with the reference line. It is 98. We subtract this value from the total number of divisions. That is 100 minus 98, giving us 2. Multiply the answer by the least count and assign a negative sign, so we shall have negative 0.02 millimeters. This screw gauge will give a reading that is 0.02 less than the actual measurement. To measure the diameter or thickness of a wire using a micrometer screw gauge, first we find the least count of the screw gauge. In this case, it is 0.01 millimeters. Then we determine whether there is a zero error. This one has a positive zero error. The coinciding head scale reading is 5. So zero error is equal to 5 times 0.01, which is equal to positive 0.05 millimeters. Observed reading is equal to main scale reading plus the head scale reading times least count. The actual reading is equal to the observed reading minus the zero error. We place the wire in between the stud and the flat end of the screw and turn the ratchet clockwise to hold the wire gently between the stud and the flat end of the screw. The main scale reading is 3. The coinciding head scale reading is 55. So the observed reading is equal to 3 plus 55 times 0.01, giving us 3.55 millimeters. So the actual or true reading is equal to 3.55 minus plus 0.05. That gives us 3.50 millimeters. Next, we talk about significant figures. Now, how many people are in this crowd? Can we say about 10,000? How about 10,400 or 10,472? When we participate in measurement, we have to be aware of some limitations. We have to be careful not to make an estimate that is more precise than our measuring abilities allow. So when we use measuring devices, we only estimate one digit further than the level of precision inherent in the instrument. Consider this brick. When we measure its length, we notice it falls between 15.4 and 15.5 centimeters. The level of precision of this device is 1/10 of a centimeter or 0.1 centimeter. In other words, this instrument can accurately measure up to 1 decimal of a centimeter. So the distance between 0.4 and 0.5 can only be estimated. For example, we can estimate this length to 15.45 centimeters. In this measurement, 15 in the whole number and 4 in the decimal part are certain. But the 5 in the decimal part is uncertain. It is uncertain because it is an approximate value. The number of digits in a measurement which are certain plus one additional digit are together known as significant figures. Accordingly, we cannot estimate this length to 15.45326. We will be way off the limit because we do not have access to that kind of precision. We only estimate 1 decimal further than the least count. So any measurement will have a certain amount of significant figures associated with it that display how precise it is. Here are the rules for determining how many significant figures are in a number. 1. Any digit that is not 0 is significant. 2. Zeros in between other non-zero digits are significant. 3. Leading zeros, ones that come before the first non-zero digit, are not significant. 4. Trailing zeros, those that come after the last non-zero digit, are only significant if they are decimal zeros. This is the most confusing part, but it is easy to see from the examples. So 10,000 only has one significant figure, which really means it's about 10,000 people. It is an estimate. If we bring back the same crowd and one person shows up, can we estimate 10,001 persons? No, we will still say it's about 10,000 people because we have only estimated to one significant figure. Now, when we do calculations, we have to pay attention to significant figures. If we are adding or subtracting, our answer should have as many decimal places as the value with the least number of decimal places, unless the question has specified the number of decimal places the answer should be rounded off to. In this case, our answer should have 1 decimal place. If we are multiplying or dividing, our answer should have as many significant figures as the value with the least number of significant figures. Again, unless given specifications. In our case, our answer should have 3 significant figures. Whatever our answer is, we will have to round off to the appropriate digit. 5 or higher means we round up, 4 or below, we round down. For example, 250,700 to 2 significant figures. We count from left. 1, 2. The digit after is 0. It is less than 5, so we round down, and we have 250,000. To 3 significant figures, we count 1, 2, 3. The digit after is 7. Add 1 to 0, and everything beyond that becomes zeros, so we have 251,000. Now, suppose you get an answer like this, and you are required to get it into 4 significant figures. 25 has only 2 digits. Luckily, they are both significant. Where do you get the other 2? Remember, trailing decimal zeros are significant, so we shall put it as 25.00. Next, we talk about standard form. Now, trailing zeros in a whole number with no decimal shown are not significant. So, writing 450 indicates that the 0 is not significant and there are only 2 significant figures in this number. When a decimal is shown, the 0 becomes significant. So, writing 450 point makes the 0 significant. However, placing a decimal at the end of a number is not usually done. Consider this number again, 250,700. According to the rules we've just seen, this number has 4 significant figures because the trailing zeros are not significant. But if we add a decimal at the end, the zeros become significant. Suppose you want to write this number to 5 significant figures. What will it be? How about 6 or 7 significant figures? You will realize there is usually a lot of ambiguity when we have trailing zeros lying before an understood decimal. To remove this ambiguity, numbers are reported in what we usually call the standard form or scientific notation. Standard method is just a way of expressing very large numbers or very small numbers. Consider this number 32 million. We can write it in expanded form as 32 times 1 million. In fact, this number is similar to 3.2 times 10 million, right? Right. The figure 10 million can be written in exponential form as 10 raised to power 7 or 10 multiplied with itself 7 times. So our number can be written as 3.2 times 10 to power 7. The power of 10, in this case 7, is equal to the number of steps the decimal point moved from 32 million to 3.2. Remember, for this number, there is a non-decimal here, so it moved 1, 2, 3, 4, 5, 6, 7 steps to the left. This is called standard form. The general format for writing numbers in standard form is a times 10 raised to power n, where a is greater or equal to 1 but less than 10. In other words, a can be any number from 1 to 10, but 10 is excluded. N is an integer and is equal to the number of steps the decimal moved. So, 5,749,200 written in standard form The number between 1 and 10 will be 5.7492. The decimal moves 1, 2, 3, 4, 5, 6 steps to the left, so times 10 to power 6. That is for numbers 10 and larger. How about numbers less than 1? Consider this number. Mathematically, this is the same as 32 over 100 million. In fact, this is the same as 3.2 over 10 million. We can write it in expanded form as 3.2 times 1 over 10 million. This part can be simplified to 1 over 10 raised to power 7. If we get the reciprocal of this part, we know the sign of 7 will change to a negative. So our number can be written as 3.2 times 10 raised to power negative 7. This is also standard form. The only difference is that we have a negative power. And the reason is the direction that the decimal has moved. For our first case, the decimal moved 7 steps to the left. The power was positive. In the second case, it moved 7 steps to the right. The power is a negative. When writing numbers in standard form, for numbers 10 and greater, the decimal always moves leftwards and the power is a positive. For numbers less than 1, the decimal moves to the right and the power is a negative. So 0.002541 in standard form. The number between 1 and 10 will be 2.541. The decimal moved 1, 2, 3 steps towards the right, so times 10 raised to power negative 3. It's that simple. We use standard notation to express the submultiples and multiples of the SI units of measurement. Consider this table that we had for the multiples of the meter. Take millimeter for example. It says 1 millimeter is equal to 0.001 meters. We can express 0.001 in standard form. This will be 1.0 times 10 raised to power negative 3. And since this 1.0 doesn't make any difference, we often omit it. So we have times 10 raised to power negative 3 meters. Take kilometer. It says 1 kilometer is equal to 1,000 meters. We can write 1,000 in standard form as 1.0 times 10 raised to power 3. Omitting this 1.0, we have 10 raised to power 3 meters. If we do the same for all the other multiples and submultiples, we have a table like this one. Finally, estimating the size of a molecule in the laboratory. Now, to measure very minute lengths such as the diameter of a molecule, we cannot use instruments such as those we have just discussed. Special microscopes are used, but even they have certain limitations. We can use a simpler method to estimate the size of a molecule. We take some oleic acid, which is a soapy liquid with large molecular size of 10 raised to power negative 9 meters on a nanometer. We take water in a large trough and sprinkle some lycopodium powder on the surface. This is a greenish-yellow powder that spreads uniformly throughout the surface of the water, forming a thin layer. We then add 1 drop of oleic acid onto the surface. The oil spreads out into a thin, large and roughly circular film which is 1 molecule thick on the surface of water by pushing away the lycopodium powder from the point where the drop lands on the surface. This makes the circular film of the oil identifiable on the water surface. We then measure the diameter D of the circular film to determine its area A. If the volume of the drop is approximately V cubic centimeters, then we can estimate the diameter H of the molecule as follows. Area A is equal to pi times half diameter squared. Volume is equal to A times thickness. This thickness is that of one molecule, so H. Therefore, V is equal to pi times half diameter squared times H. That gives us pi d squared over 4 times H. And so H is equal to 4V over pi d squared. By counting the number of drops that make up 1 cubic centimeter, we can determine the volume of a single drop. For example, here, I counted 27 drops that make 1 cubic centimeter, and that means one drop is equal to 1 over 27 cubic centimeters.